All right, so let's begin with doubts and discussions from worksheet number 3 of calculus, which I had sent earlier. Okay, so let's go through the worksheet and few of the questions in it. Just go through the first question and tell me if there's a doubt in any of the parts. Okay, D part, let's start with this then. Okay. So y is equal to square root of 1 plus x square, right? And we want to find the value of the derivative at the point x equal to 2. Let's quickly work out this question. Find that is the same thing as the slope of the tangent. The value of the derivative at x equal to 2 is the same thing as slope of the tangent at x equal to 2. So we have to differentiate this. So as you can see, this is a composite function. This is a function of the type f of gx, where gx is 1 plus x square. So f of gx is square root of gx, which is square root of 1 plus x square. So to find dy by dx, we'll have to use chain rule.
So, sir, we'll first solve the square root part and then 1 plus x square.
Can't hear you, but speak a little louder, please.
So here in this case, first we'll solve the square root and then 1 plus x square.
Your audio is not clear, but come closer to the mic and speak.
So can you hear me clearly?
No, your voice is very soft, but I can't hear you clearly.
So now?
You have to come closer to your microphone, whatever device you're using. Speak closer to the microphone.
Yeah, now? So now?
No, it's the voice is coming broken.
Sir, I can hear him.
Yes, sir. Thank you.
Is my voice clear?
Yeah, Dharmik, your voice is clear, but it's very low in volume. Yeah.
You can increase that audio in your settings.
Yeah. Dharmik, you can increase the audio volume in your settings.
No, sir, no, sir. We can hear him. You are not able to hear him.
I can hear everybody else. I cannot hear him only.
Okay.
Yeah. Okay, anyway, so try again. Come closer to your mic and speak loudly.
So now?
Yeah, okay, try now. Yeah, what is the doubt? Better speak.
No, sir, I was telling first we'll solve the square root part and then go for it.
I'm not able to understand what you're saying, better.
Sir, he's saying that first we will solve the square root part and then 1 plus x square. That what?
Yeah, I'll explain that out. Yeah. Yeah, first we'll solve the square root part means first you will do substitution actually. Okay? As
yes.
The step-by-step method that we've learned. Okay. So do the substitution. So it's actually first you have to substitute the quantity inside the square root, right? Not solve the square root, but So first we have to solve, you have to substitute the quantity inside the square root. So take z, let's say, as 1 plus x square. So then you can substitute y as square root of z. So then your next thing comes in, the chain rule step. That is dy by dx will become dy by dz into dz by dx. So this is where your differentiation of the square root function comes in. Okay. Y is square root of z, so differentiation of that is 1 by 2 z to the power minus half. Okay. And z itself is 1 plus x square, so its differentiation is 2x. So this becomes x by root z. Okay, that's my dy by dx. And now the last step, we have to do the resubstitution. So we have to resubstitute the value of z as what? 1 plus x square.
Two upon root 5.
Yes, very good. 2 upon root 5 is the correct answer. So now this is dy by dx in general. Now we have to find the value of the derivative at the point x equal to 2. So for that, just substitute. So dy by dx at x equal to 2 will become 2 upon square root of 5. So 2 upon root 5, that becomes our final answer.
Sir, now is my voice coming?
Yes, now it is coming.
Oh,
You have to speak consistently loud. That's the only thing. People who are not used to speaking on online platform, what happens is your voice tends to be loud and then again soft and again loud. So you can hear intermittently.
so now my voice is not coming loud.
Now it's loud. Now it's proper. Yeah.
Okay, sir.
Okay. So anyway, hope this question is clear, right, to all of you. Okay.
Yes.
Let's look at the worksheet again. So any other doubt from question 1 for anyone?
No, sir.
Okay, very good. I have sent you the hints also along with this, so it should be okay. Let's come to the second question. Any doubts from this?
No, no, sir.
Okay, good.
I have a doubt in the
Sir, D.
Which part, beta?
Sir, D.
D part. No, okay. Yeah, D part is again that slightly lengthy type of question. Why it is lengthy is because see, it is a product of two functions. Okay, and one of them is a what type of function? Composite function. Okay. So what we have to do is, let's say this is fx and this is gx. So we have to use the product rule first of all. So dy by dx will become derivative of this function into g plus this function into derivative of g. But for calculation of derivative of g, we have to use the chain rule method, right? So f we can see over here is square root of x. So derivative of f is very simple. It is 1 by 2 root x. Okay. But when it comes to the term of g, it's a little bit more complicated. G is 1 plus x squared to the power 3 by 2. So we can write g as z to the power 3 by 2, where z is equal to 1 plus x squared. So the derivative of g will become derivative with respect to z into this. Okay. So this is our chain rule application. So as you can see, this will become 3 by 2 z to the power half into differentiation of z, which is 2x. Okay. So this will become how much? This will become 3x into root of z, and z itself is 1 plus x squared. So from this analysis, what we are getting that our derivative of g is 3x square root of 1 plus x squared. Is this step clear?
yes, sir.
Yes,
Okay.
sir.
So once this step is clear, so it's useful to do this separately. Now you can just substitute this back over here. So dy by dx क्या बन जाएगा? f prime, which we have seen as this. So 1 by 2 root x into g. Now g is what? 1 plus x square to the power 3 by 2. Okay. So this whole thing plus f, which is root x, okay, into g, g prime, which is this 3x into square root of 1 plus x. Okay. And then also what you can do is like these terms, you can take square root of 1 plus x square common. So simplify it a little bit further. So I'll
1
just,
plus 7x square square root.
yeah,
1 plus x square upon 2 root x.
yeah. So I correct, very good. So I'll just simplify it for you. So we had y was equal to root x into 1 plus x square to the power 3 by 2. So what we did is we took this as f and this as g. So we saw f's derivative was this, g's derivative was 3x into 1 plus x square to the power half. This came using chain rule. Using chain rule. So once you got this, now we can see that by product rule, dy by dx, it is differentiation of f into g. So it will become differentiation of f into g plus f into differentiation of g. So plus root x into 3x into 1 plus x squared to the power half. Yeah, so what do we take common now? We can take square root of 1 plus x square common, right? So this term will become 1 plus x square by 2 root x, okay? And this term will become 3x root x, right? And then further we can take LCM. So we have square root of 1 plus x square upon 2 root x, 1 plus x square plus 6x square will have. Okay. So ultimately we'll have
1 plus 7.
Yes, 1 plus 7x square into square root of 1 plus x square divided by 2 root x. Okay. Even some more simplification can be done, but I'm leaving it at this step. More simplification means you can take the square root common in this numerator and denominator also. So, you know, this is the maximum lengthy sort of question you can have involving differentiation. Right? So hope all the steps are clear. Just let me know if there's any doubt.
So can you show the fifth one?
Which one, beta?
Fifth question.
Fifth one.
The gas cylinder.
You mean the fifth part of this second
Sorry,
question?
the fifth
Question
question.
number 5.
Question number 5.
Question, yeah, I'll come to that. So anything else in question 2, all the parts are clear now?
Yes, sir.
Okay. Moving on to question 3, it is clear?
Yes, sir. For the first, sir, for the first question on question 3, we just have to substitute the values of x,
Yes,
right?
yes. So you have to find the value of y at different points. Calculate the values. This is not value. That's a spelling mistake. It's a values. Okay. Values of y at this point. So for example, at x equal to, let's say, -3, the value of y will become how much? Just substitute x as -3. So -3 to the power 4 minus 2 into -3 square. So that will become 3 to the power 4.
60.
So 9 9s are 81, right? Minus 9 into 2, 18.
63.
So this becomes how much? 63.
63.
Sorry. Right. So this kind of thing. So like that for each of these points. So this is a very lengthy question in that sense. For each of these points, you have to sit and calculate this. So when you do that, you get that kind of, and then when you plot an approximate graph, you get
It is
that
same
kind of,
for the negative and positive values.
yes. That's a very interesting thing. It's the same for negative and positive because we have only even powers. So that's why the graph comes out to be like a W shape, like this.
Yes, sir.
Comes out to be with respect to the coordinate axis. Comes out to be something like this. This point is actually exactly 0. Okay. So for example, you can see here, if we take this point as -3, its value is very large over here, somewhere here. it's 63 or something, but it will have the same value at +3 also. Okay. Similarly, what you will see is that if you take the value at -1, its value will be how much? -1, and again at 1 also its value will be. Whereas at 0, its value is 0 like this. So it has an interesting kind of shape like this. Okay. So anyhow, so I think if you just go through the detailed solution I have given of this now, it will be clear how to do the plotting of the graph also, and slope of tangent. Obviously, you know how to find at each point. So you have to just find dy by dx and put the value of x as this, not in y but in dy by dx for slope of tangent. Right. All right. So moving on. Next up, let's question 3. What about that? That is clear.
Yes, sir. It's just like chain rule.
Yes, it is actually chain rule. मतलब directly आपको chain rule ही use करना है उसमें.
Yes, sir.
Right. Okay. Question 4.
Yes, sir.
So anybody has a doubt in question 4, any of the parts?
No, sir.
Yeah.
No, sir.
Okay, good. Equation of tangent also you understood now how to find. Okay. Good. Yeah. Question 5. Somebody was asking. Now, who was asking question 5?
Sir, me.
Yeah. Okay. Yeah. Better. So we'll discuss question 5 in detail. So this is like a practical sort of application of rate of change concept or calculus concept in a practical physics type of situation. So what is happening is you have a cylinder which is initially empty at t equal to 0. Okay. But then you are pumping in gas at the rate of 4 plus t grams per second. So this rate is given in what? In terms of mass per unit time. Okay. And right from the start, there is also leakage in the tank. So there is a leakage at the rate of 2 grams per second, whereas you are pumping in gas at a rate which is increasing with time, because you can see it's 4 plus t. No? So the rate of pumping at t equal to 0 is 4 grams per second. But by the time you come to 1 second, it's become 5 grams per second. At 2 seconds, it's become 6, like that. So your rate of inlet pumping, or the inlet pipe is, let's say, pumping in gas, that is increasing with time. Whereas the leakage is a constant rate of 2 grams per second. So first of all, we have to find the net rate of, okay, with which the gas changes in the tank, the mass of gas, and then based on that, few more things. So we'll discuss this question. So what all we have to find? Net rate, then total mass as a function of time, and we have to plot the graph of approximate graph of mass versus time. Okay. So let's visualize this question a bit more detail. Okay, so let us say this is our approximate diagram of our gas cylinder. Let's see. Now, first of all, at t equal to 0, the mass of gas in the tank is 0. Okay, the tank is empty. But right from t equal to 0, there is an inlet or some mechanism of a pump which is pushing in gas at a certain rate. So it pumps gas into the tank at a rate of 4 plus t grams per second. Okay. So if I take the mass of gas in the tank after some time, at time t equal to t, if I take the mass of gas as m, so this is what we call the instantaneous mass. So why instantaneous? Because it is changing with respect to time. So at that instant, it is some m. Then we can see two things are happening. One is that there is some leakage happening somewhere. So leakage is happening at the rate of 2 grams per second, and the other is gas is being pumped in. So we can understand that the rate of change of this, that is the net rate of change, of mass of gas with respect to time. That will be equal to what? It will be equal to positive of the rate of pumping in minus of the rate of leakage. Okay. So dm by dt, the rate of change of mass, is equal to 4 plus t minus 2. This is in grams per second. So the rate at which the mass of gas is changing in the container as a function of time is 2 plus t grams per second. So this was in fact the first of the questions directly asked. Okay. And from this now we have to also find out the formula or the expression for mass of gas as a function of time. So far it is clear, no?
Yes, sir.
So net rate at which mass of gas in the tank increases as a function of time. You can see it's a positive quantity, so it's increasing with time. Okay. Had the rate of leakage being more, then it could have been a negative quantity also. But here the rate of inlet is more than the rate of leakage. So it's a positive quantity, so mass is increasing with time. Now comes the tricky part of the question. We have to find now from this instantaneous mass as a function of time. So here our experience of differentiation comes into play. So what we observe, what information we have about this instantaneous mass. First information we have is that the value of mass at t equal to 0 was 0. Okay. At t equal to 0, the value of mass was 0. So that is one information I have. And the second information I have is that dm by dt is 2 plus t, which if you observe is a linear function.
Yes, sir.
So now you go back to calculus and you understand that if your derivative of a function is linear, then what can you tell about the function itself? Differentiation results in what happens to the power in a polynomial function. It becomes one less, no?
Yes, sir.
So that means fx कैसा function होना चाहिए? अगर f prime x linear है, so maximum power is 1, then fx कैसा होना चाहिए? It should be a quadratic function. Okay, this point is clear.
Yes, sir.
Yes.
So if we differentiate a quadratic function, we are getting a linear function. So since here dm by dt is linear, it's a linear function of time. Okay, here the variable is time. So what that tells us, that means m must be a quadratic function of time. So what we can do is, let's start by assuming it is something like this: at square plus pt plus c, where a, b and c, they are unknown, but they are constants. There are some unknown constants. So now we need to calculate the value of abc. Okay, so far it is clear.
Yes, sir.
So now see three things which are unknown, a, b and c. इनको हम कैसे calculate करेंगे? So first is we'll use this information, that in this function m at t equal to 0 should be 0. So substitute that. So a into 0 plus b into 0 plus c should be 0. So that tells me that c is equal to 0. So one of the three things I've got, a, b, c. Okay. Now, and the second thing that I know is that dm by dt, the instantaneous rate of change, should be 2 plus t. Okay, so differentiate this function. Okay. Now this function has become at square plus dt because c has already become 0 above. Okay. So this should be how much? This should be this. So a is a constant, b is also constant. So this should be equal to 2 plus t. Now if you compare the two sides of the equations, I mean the equality sign, you see that both sides I have a linear function of time. So the coefficient of t must be same on both sides. So
Yes.
2a must
1.
be equal to 1, which means a must be equal to half or 0.5. And b must be equal to 2. So now I've got these two also. I've got the value of a, I've got the value of b, c I already had. So now I know that mass as a function of time is how much? It is A, or 0.5 t square plus bt, that is 2t, plus c, which is 0. So this must be m in grams. Okay. So mass is in grams and time is in seconds in this. And now you can just double check that if you take this the value of m, you will get your dm by dt as 2 plus t. If you just differentiate this, you can see you will get 2 into 0.5, that's 1 into t, plus differentiation of 2t, that's 2. So that's it. That's t plus 2, which is the same thing as
So
this.
yeah, 2 plus t is equal to the derivative of a t
Yeah.
square plus bt.
Yes, because see, what is 2
Okay.
plus t? It is rate of change. Na? Yahan pe dekho.
Okay, sir. Yes.
This is
got it.
dm by dt. How we know this? We came to know this from the earlier thing, that this was the rate of pumping in minus the rate of leakage. So that gave us what? Rate of change of mass. Na? So that's dm
Yes.
by dt. So now if I assume mass is some kind of function of time, then obviously dm by dt is the derivative of that function. Na? So this derivative is linear. Okay, so that means this must be quadratic. So that's the idea that I'm using here.
Okay, sir. Yes.
Sir, could you just scroll up?
Yes, any other doubt? Somebody?
Can you scroll up, sir?
Yeah.
Sir,
Yes.
sir, I have to see the last part, that 2D.
Which last part?
Sir, of question number 2D part.
Okay. Okay.
Sir, and one more request. Can you just send the hints or the answers of all the worksheets in the group again?
All the questions in?
No, sir, all the answers and hints in the greenhouse group again.
Acha, again. Okay. Okay.
So after the class, it's okay. You can send it tomorrow or day after
Yeah.
that.
Yeah. Okay. 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 You have the worksheet now?
Yes, sir, I have the questions. I just needed the hints and the answers to just to
Okay.
cross-check
Okay.
and-
Because I think I had sent the answer key and the worksheet together, but I'll send it again then.
Yes. Yeah.
Okay.
I'll once check if I have the answers or hints.
Okay. I'll send it again. Don't worry.
Okay, sir. Thank you.
Okay. Okay. So this is clear, na, the whole thing?
Yes,
Yes,
sir.
sir.
Okay. Now let's go to that other question. Question 2, last part. Na? Okay, just a moment. Yeah, this one. This one, right?
Sir, no, I have to copy that 2D which you have solved. Not
Acha,
this.
2D. Okay. Okay. Sorry. I thought you were asking another question. 2D we've already solved, na, that one. Okay. Yeah. Yeah, this one. So here I have not given this part in detail. Okay, this how we got this. G is 1 plus x square to the power 3 by 2. So in this we substitute 1 plus x square is z. So G becomes z to the power 3 by 2. And then you use chain rule. The derivative of G becomes, so that becomes 3 by 2 z to the power half into dz by dt, which is 2x. So when you resubstitute that, you get this. Okay.
Okay, sir. Thank you. Sir, it's done.
Okay, done now? Okay. Yeah, I have just resent the worksheet along with the solutions on the group. So in case anybody has lost the worksheet or solutions, you can download it again. Okay. Now let's come to the next part of differentiation. So we will see application of differentiation. to analyze functions. So I'll explain by what we mean analyze. Okay. So the first aspect of a function that we can analyze is that given any function y is equal to fx, by calculating the sign, that is positive or negative, of dy by dx at a certain point, okay, we can analyze if the function is increasing or decreasing at that point. Another way of expressing is this is the graph is rising or dropping. So this is actually best explained by showing it on graph itself. So suppose I have some kind of function which when I plot the graph over certain range of x or certain set of values of x, I see the function is having this kind of behavior, that it's rising and then dropping and then maybe rising again. So what I'll be able to understand is that if this is some point x1, let's say, and I draw a tangent at this point, this tangent at x1 this will have a positive slope. Whereas suppose I select another point, let's say x2 over here, you will see by contrast the tangent drawn at x2 will have a negative slope. So now the thing is, if I have a function whose graph I don't know, then I can get this information about the graph, that where the function is rising and where it is dropping. Okay. So basically what this means is that for y equal to fx, if f prime x is positive at x equal to, let's say, x1, that means the function is, in short form, we'll write like this, rising. So rising means that the nature of the graph is such that y increases with x increasing at x1. Okay. And if f prime x equals to a negative quantity at x equal to x2, then now that implies that the function is dropping, or what we said, decreasing at x equal to x2. Okay, so just make a quick note of this concept, then we will see how we use it. Okay. So here the graph is shown to you just to show you the meaning of this term rising and dropping, but actually how we'll use it is, suppose we are given a function whose graph we are not aware of, then we can understand something about that unknown graph by using this property, that for which values of x the graph should be rising and for which values of x the graph should be dropping. So that can be analyzed by using this information.
Yes, I know.
Okay, so this point is clear to all of you, that you can see the shape of the graph. So the graph can have, it can be a situation where the function only does this, so it's only increasing everywhere. It can be a function where it's only decreasing everywhere, or it can be a function which is almost like a wave, so it keeps rising, dropping. So there are any number of points where the function is either having a positive slope or a negative slope. So that depends on the nature of the function. But if we know how to differentiate the function, then we can easily calculate that whether the function is increasing or decreasing at a point. So that is the analysis of the function that we can do using differentiation. Hence the term application of differentiation to analyze the function. So let's understand this with a simple example to start with. So suppose given a function. Sorry.
Sir, will we do integration today?
No, but integration is still some time off, because we have to first do application of differentiation including local maxima and minima. So this will take a couple of lectures and then we'll come to integration, right?
Okay, sir. Thank you.
Okay.
And
But you will
sorry
find
to disturb you.
integration relatively easier than differentiation, because I mean, integration is actually the same kind of thing as differentiation, but it's like the reverse operation of differentiation. So once you've got familiar with differentiation, you will find integration much easier to understand. Okay.
Okay, sir. Thank you.
Okay. So don't worry about integration. Now we'll do everything in detail. Okay. So now suppose we have a function like this: y is equal to 4x minus x squared. Okay. And we want to find the set of values, or in maths sometimes we say that intervals. Find the set of values of intervals of x for which y increases with respect to x. Okay. And secondly, for which y decreases with respect to x. I'm going to find this. So basically we have to just interpret it in such a way, it's very simple, that y is some kind of function of x here. So f prime x is positive for a certain interval, let's say. That means y increases for that same interval. Okay. And f prime x is negative for a certain interval, let's say c to d, whatever. Okay. That means y is decreasing for that particular interval. So just in language of calculus, this whole question just becomes this. The meaning of the question becomes this. So this is what we have to do here. So the function we can see is 4x minus x squared. So the derivative of the function dy by dx or f prime x, we can see is 4 minus 2x. Now we can see this, that dy by dx is positive when 4 minus 2x is greater than 0. That means 2x is less than 4 or x is less than 2. So we can say that for any value of x which is between minus infinity to 2, what is happening? Dy by dx is positive. So that means y is doing what? Y is increasing with respect to x. And similarly, we can also see that dy by dx is negative when 4 minus 2x is less than 0. That means 2x is greater than 4 or x is greater than 2. So that means that for any value of x which is in this interval, okay, the derivative dy by dx is negative, okay, which means that y is decreasing. So if we think in terms of behavior of the function, we may not have plotted the function yet, but we'll understand one thing, that in terms of x-axis, we can see that the point 2 becomes a very critical point for us. Because what is happening, the function has a nature that it is rising up to 2 and after 2 it starts dropping. Okay, so the function is increasing with respect to x here, and it is decreasing with respect to x over here. So next, maybe we can even plot the graph of the function with some extra information. But at least this thing is very easy to find out. So the question was this, that we wanted to find out the interval of x for which the function is increasing or decreasing. So we can see that over here. Okay, this is the interval where the function is increasing. We have first found that out. So this is the interval where the function is increasing. This is the interval of x for which y is increasing. And similarly, this is the interval where y is decreasing from 2 to infinity. Of course, as some of you might have noticed that we are also having a third case where dy by dx is 0, and that is happening at a particular point x equal to 2. So that also becomes a very significant point for us, and we'll discuss about that next, because the behavior of the function switches from increasing to decreasing. Okay, so that's a very critical kind of a point, and we'll discuss about that also. But first things is that analysis of the interval where the function is increasing, the interval where the function is decreasing.
So in the first case, where it is the values of x are from minus infinity to 2,
हाँ,
isn't the function decreasing or decreasing to
नहीं
like
बेटा,
from minus
derivative is
infinity to
positive ना. अभी आप करके देख लो ना. Let's take
okay,
some
okay,
values. Okay.
if the derivative is okay, yeah.
But let's also check it out. Na? Like tell me some values of x which are less than 2. Let's try this out. Na?
Minus 10,
Minus 10 ले लो, फिर 1 ले
1,
लो.
0.
Okay. और let's say minus 10 के बाद minus 5 ले लो, ना? फिर 1 ले लो, या फिर 0 ले लो, फिर 1 ले लो. Okay. So what is the value of y at this point? Now tell me at minus 10 how much y is?
24.
Huh?
20.
It's minus 40, minus 100, na?
Okay.
So it's minus 140. Is that correct?
Yes, sir.
Yes, sir.
Okay. Minus 5 पे कितना है? Minus 20, minus 25.
Minus-
So minus
Minus.
45. Okay. So you have seen y is increased.
Yes, sir.
Minus 140 is a smaller number than minus 45, no? Because you're taking sign into account.
Yes, sir.
फिर
Okay.
0 पे कितना हो गया? 0 पे 0 हो गया. 1 पे कितना हो गया? You'll see it will further rise. 4 minus 1. So it's become plus 3. So you can see y is increasing. But now you take some values of x after 2. Like take x equal to 3, let's say 5, 12, something like this. You'll see what is y. You'll see it has a decreasing trend. See, 12 minus 9. So कितना हो गया? 4. Sorry, 3. Okay. Then 20 minus 25. So minus 5 हो गया. And then 48 minus 144. Okay. So that is how much? 48 minus 144 will be minus 96.
minus
So you can see that y is decreasing. Now, how we know exactly which is the point where it is switching from increasing to decreasing? So one is we could have taken more number of values and checked out, but that would be a very lengthy process for us. Na? तो यहाँ पे मुझे दिख रहा है that between 1 and 3, somewhere it must be switching behavior. Because up to 1 we are seeing it was increasing, and after 3 we are seeing it's decreasing. But that point could have been 1.5, that point could have been 1.03, that point could have been 2, it could have been 2.5. So how we know exactly is the point 2 where that behavior is switching? So we know that from this analysis. So it's like an investigative tool, this differentiation, the derivative of a function, it helps you investigate this type of behavior of the function, where the function is rising and where the function is dropping. And it's something very easy to keep in mind, because all you have to do is visualize a graph. In any graph, if the function has an increasing nature somewhere, you can see that the tangent will have a positive slope. If it has a decreasing nature somewhere, it will have a... So here the graph must be looking something like this. It must be shaped like this. And this must be the point 2. Up to 2 it is rising, and after 2 it is dropping.
So by finding the derivative, we know the range of x.
Range as in?
If like for y to be less than 0, then we can find the
dy
derivative.
dy by dx to be less than 0. Or you're talking about the function's range?
Function.
Function's range, beta, we have to find the set of values of y now. So that is where this will help us understand actually.
So in the question they asked that need to find intervals of x for which y increases.
Huh.
So is that with respect to the function or derivative?
No, that is with respect to the function. No? Y is the value of the function. No?
Huh.
So this question here is with respect to the function. No? So given y is related to x like this, that it's 4x minus x square. So I want to find the intervals in x for which y increases or decreases. So there y is which quantity? It is 4x minus x square. No?
Huh. Okay, okay, sir.
Got it? No, it's not 4 minus 2x because that is the derivative. Y is how much? It is 4x minus x square.
Sir, so what's the use of finding the derivative?
उसी से तो मुझे पता लगा ना कि where the derivative is positive and where it is negative. Otherwise, how I have analyzed this thing that up to 2 it is increasing and after 2 it's decreasing. How we got this? See, this interval.
Okay.
How did we get this over here? This is the answer to the question, no?
Okay, sir.
That for x belonging to the interval minus infinity to 2, the function is increasing. And for this, we got the answer that for x belonging to 2 to infinity, the function is decreasing. But how we got this? We got this by analyzing this information. This was the method that we used for it, this method.
Okay, sir, understood.
Understood? No? So now
Can
see,
you
using
scroll
this,
up?
yeah. So this is not the graph of the function, okay? This is just a number line plot to show what is happening to y with respect to x. That y is increasing up to x equal to 2 and after x equal to 2, y is decreasing. Okay, so
Yes, sir,
this
got
is
it.
done. Yeah.
Yes, sir. So, sir, this will help us to calculate, know if the function is increasing at a certain point by just substituting the value of x by in its derivative without having to
Yes.
calculate the function itself.
Exactly. Without having to plot the graph of the function, no, we can just understand the trend of the function at a point, whether it is increasing or decreasing, okay, by calculating the value of the derivative, whether it is positive or negative. Okay. Now,
Okay.
for example, for this function only, it can help us analyze it further. Like if we see this function that we just analyzed. So what we understood here that for x from minus infinity to 2, y was increasing, and for x from 2 to infinity, y was decreasing. Now, in addition to this, if we also calculate at x equal to 2, what is the value of y? So just calculate, it's 4 to the 8 minus 4. So it's plus 4. Okay. And also at x tending to minus infinity, what is y equal to? So 4 times minus infinity minus of minus infinity squared. So y will also tend to minus infinity.
Yes, sir.
You can just analyze with like take a value of x like minus of 10 raised power 3. So y will become how much? It will become 4 into minus of 10 raised power 3 minus of minus 10 raised power
Raised power 6.
so square. So it will become like minus 10 raised power 6 minus 4000. So it's like minus 104000 something like this. So it's a huge negative number, no? So it's like that. But similarly, if you analyze at x tending to infinity, what is the value of y? Can you tell me?
Tends to minus infinity.
Again, it is minus infinity only. Like take the value of x like 10 raised power 4, for example. So y will become 4 times 10 raised power 4, but minus 10 raised power 4 squared. No? So it is minus of 10 raised power 8 plus 40,000. So it is like minus of 906000 something like this, I think. So it's a very large negative number. So it tends to minus infinity because the minus x squared term dominates over the 4x term, basically. Okay. So now, in addition to this information that I had earlier, that is increasing and decreasing, now if I use this information also, then you can see I can get a pretty accurate plot of the graph. Okay. So at this stage for us in basic calculus, graph plotting is not exactly something that we require. Okay. In advanced calculus in maths, it will become a whole subject for you, whole part of the subject for you. But even if you need to analyze the shape of the graph, this can come in very handy. So you can see at the point 2, the value of the function is, let's say, 4. I mean, the value of the function is 4. Let's say that's here. Okay. But at minus infinity, it's starting from minus infinity, and infinity is going to again minus infinity. So the shape of the graph should be like this. In language of maths, we say this is an inverted parabola, or it's a parabola opening downwards. This kind of a curved shape of a quadratic function is called a parabola. Okay. And the mouth of the parabola is opening downwards, you can see. So it's a downwards opening parabola. So this is the graph of this. So if we had actually plotted, I mean, points, using our earlier method, we had taken some 10, 20 different points and plotted them, you would have got this shape. But now we are getting it much more easily by just using this information along with this information. So now from this, we can see one more interesting thing here. What we can see is that for x going all the way from minus to plus infinity, y only ranges between minus infinity and 4. Y never increases beyond 4. And this 4 we should use with a closed bracket to show that y is less than equal to 4, but never greater than 4 when I take x between infinity and minus infinity. So this is also kind of showing you that the values of y is limited over here. No matter what value of x I take, my y will never increase beyond 4. Okay, just make a note of this. I'll just be back. Okay, so now this kind of analysis gives us a lot of interesting data about functions. For example, now if I take a function which is having more degrees, okay. So let's take as an example a cubic function. Now suppose I have y is equal to x cube minus 3x. And I want to analyze for the intervals of x for which y is increasing and decreasing. So the same process I have to repeat, but it's going to be a more interesting question to solve because the function is now a cubic function instead of a quadratic function. So a little bit more analysis will come in. So I want to do this, and I also want to plot an approximate graph. So for this, use the intervals from part 1, okay, and also analyze values of y for x tending to plus or minus infinity. You have to make use of all this information. Okay. So just try this out, people. Try to repeat the steps that we've done in the previous question. Okay, but with a little bit of extra maths involved because this is now a cubic function. So the derivative is going to be a quadratic function for us. Okay, so is that extra bit of work involved in it? Yeah, once. So the answer that you have sent me is for y to increase with respect to x, or for dy by dx to be greater than 0, right?
Yes, sir.
No, so y prime should be greater than 0. For that you send the answer, right? Okay, but there is one more interval where it's happening. It's not just 1 to infinity. There is
sir.
one more
Sir,
interval.
I'm sending that answer right now.
Yeah, work. Okay, so I'm getting very few answers which are correct. Arushi, very good. Your answers is correct. So you should be getting this. For this, x should be either between minus infinity to minus 1 or from 1 to infinity. And for this, x should be specifically between minus 1 and 1. So basically, if you do a sort of number line analysis, you will see that minus 1 and 1 are critical points for x. And as far as the function is concerned, it will tend to be rising here, then again dropping here, and again rising here. So let's start with the steps. So for first part, given that the function is x cubed minus 3x, so derivative of the function is 3x square minus 3, which we can nicely factorize and write as this. So this is where it's going to come in handy. So for y to be increasing, derivative should be positive. So 3 into x minus 1 into x plus 1 should be greater than 0. Now this is where another method of number line helps a lot. If you take values and for example, if you plot the factor x minus 1. Now for x minus 1, you can see that 1 is a critical point because for x greater than 1, this factor becomes positive. For x less than 1, this factor becomes negative. Okay. And side by side, if you also plot x plus 1, you can see for this minus 1 is the critical point. For any x less than minus 1, it's negative. For any x greater than plus 1, it's positive. So now when we look at the overall thing, f prime x, which is the product of these two, into 3 also, of course, but 3 is a positive quantity. So that doesn't really matter so much. Okay. So you can see that clearly have that in this region, f prime is positive. In this region, f prime is positive. But in this region, f prime is negative. So now if we talk about the function fx, we can see that here it is decreasing and here it is increasing. So immediately you understand this. So this gives us x is greater than 1 or x is less than minus 1. Or we can also express it this way, that x belongs to the interval minus infinity to minus 1 union with 1 to infinity. So this is the interval for y to be increasing with respect to x. And like that, minus 1 to 1 will become the interval where y is decreasing with respect to x.
So,
Yes.
so like
Yes.
even if we take suppose example as -2, then we will get y as positive only, na, because of the square.
बेटा y से नहीं, dy by dx से मतलब है ना. So dy by dx देखो कितना है, 3x square minus 2 ना.
-3.
3x square minus 3 na. So
Yes.
put the value of x as 2, see it's a positive quantity. Put the value of x as minus 2, also it's positive. But put the value of x as let's say 0.5 and you'll see it's negative.
Yeah.
Or put it as minus 0.5, again it's negative. Put it as minus 0.9, again it's negative. Right?
And so at x equals to 0, it would be again negative 5 minus 3.
It's negative, it's minus 3. So even at 0, it's decreasing na, as a function. So anything greater than minus 1 or less than 1, it is decreasing because dy by dx is negative. Got it, no?
Yes.
Sir,
Yes.
sir, can you once explain me again the graph?
ग्राफ तो नहीं प्लॉट किया बेटा अभी तक. ग्राफ वी विल कम टू. यहाँ पे क्या किया हम लोग ने, वी हैव जस्ट एनालाइज कि फंक्शन क्या है x क्यूब माइनस 3x. सो फंक्शन का डेरिवेटिव क्या हो गया 3x स्क्वायर माइनस 3. सो ये जो 3x स्क्वायर माइनस 3 को फैक्टराइज करके हमने लिखा है ना x माइनस 1 इंटू x प्लस 1. सो व्हेन इज दिस फैक्टर पॉजिटिव? सो इट्स द प्रोडक्ट ऑफ टू थिंग्स ना, x माइनस 1 इंटू x प्लस 1. So it can be positive either when both are positive, that is happening over here in this region, or it can be positive when both are negative, that is happening in this region when x is less than minus 1. So we can see that this greater than 0 will happen either when x is greater than 1. So both these factors are positive. So their product is positive. और when x is less than -1, so ये भी negative है, ये भी negative है, तो दोनों का product क्या हो जा रहा है? Negative हो जा रहा है. I mean दोनों का product क्या हो रहा है? Negative into negative, positive हो जा रहा है. Understood ना?
Okay, sir.
So,
Yes.
so we could also say that we could find this interval by Wavy curve method of maths.
In fact, this is Wavy curve method only. Na?
Yes, sir. We have been taught this.
This is another way of expressing Wavy curve method only. Na? In maths, if you've
Yes.
learned Wavy curve method,
Yes, sir.
ये जो है ना, you plot the different factors and then their product, you can see how it's becoming. That
Yes, sir. Like, yes, sir.
So this is in fact those steps only. They are steps very similar to what we've learned as Wavy curve method. Okay, so you can see the second thing's answer is also already here. Okay. A part, we wanted to find out where the function is increasing. Now B part, for y to be decreasing, okay, the derivative should be negative. So 3 into x minus 1 into x plus 1 should be less than 0. So from the above number line, you can see that that is happening for this interval. X greater than -1, less than 1, or x belonging to the interval -1 to 1. So that is what you can see in this top part. The function is increasing up to -1, then it is decreasing, then again it is increasing. So now we understand that the graph of the function, when we plot it, it should look something like this. Up to x equal to -1, it should be increasing. Then up to 1, it should be decreasing. And after 1, again, it should be increasing.
But this is for y is increasing, right?
This will be the graph of y versus x. It will be like this.
And till point -1, 1, it is decreasing.
-1 पे उसका वैल्यू कितना हो जाएगा? +2 हो जाएगा. और 1 पे उसका वैल्यू कितना होगा? -2 होगा. So it's a very symmetric graph. So this point here, it will have a y coordinate of +2, and this will have a y coordinate of -2.
So -1, we will be putting it in the x cube minus 3x, and derivative we use only for finding the interval.
Graph pe to, if you want to plot the point, you have to find the y coordinate of the point, because this is the graph of y versus x. So what is the relationship of y versus x? This is the relation. Derivative is only giving you slope of the graph. So at a particular point like x equal to -1, if you want to find the slope of the tangent, so you'll see it's a horizontal tangent. So slope is 0. At -2, for example, the slope will be positive. At 0, for example, the slope will be negative.
Okay, sir.
Understood now what the slope is telling us and what the graph is?
Yes, sir.
So anyhow, let's come to the detailed analysis of the graph. So like I can said that at this stage, graph we are doing as a sort of thing of self-interest. What is more important for us at basic calculus level is that we should be able to answer this, that which is the interval in which the function is increasing. So that is this interval, which is the interval in which the function is decreasing. So for this interval, the function is decreasing with respect to x. Now, of course, using this information and a bit more analysis, we can come to that very interesting thing where already we saw on the number line, we analyzed that -1 was one important point, +1 was one important point. Now, what was our function? Our function was x cube minus 3x. So one thing we can see that for x tending to -infinity, what will be the value of y? Again, it will tend to -infinity because the x cube term will dominate. Okay. And similarly, for x tending to infinity, y will tend to infinity because the x cube term will dominate. Okay. And the other thing is this part the graph is rising, this part the graph is dropping, this part the graph is rising again. Okay, now we can see at x equal to -1, what is the value of y? The value of y is -1 cube plus 3, so that is +2. And at x equal to +1, what is the value of y? It is 1 cube minus 3, so it is -2. Okay. And just for reference, you can also see that at x equal to 0, the value of y is 0, 0 minus 0. That will just help a little bit in plotting the final graph. So now we have got some, guidance points for the graph also. So our guiding points are these all things, that minus infinity, what is the behavior? Plus infinity, what is the behavior? At 0, how much is the value? And also these two critical points, 1 and -1. Okay. So we can see that the graph cuts the origin. Okay. Then also the graph at +1, it reaches the value -2. So let's say that's here. It's going to go through this point. Okay. Whereas at -1, so this is the point where it reaches the value +2. So it's going to cut this point. Okay. And also the graph starts from -infinity. Okay. So if it starts from -infinity, it has to have this kind of a shape. Passes through the origin, goes through this point, and now from here it has to rise to infinity. So roughly speaking, this is something like the graph. It's this kind of a shape. This kind of a shape. So here we can see that it is like a unrestricted kind of function, because as x is going from minus to plus infinity, here there is no restriction on the value of y. Y also goes from -infinity to infinity, unlike the previous one where y was going only up to 4. But at the same time, there are also these interesting things about the behavior of the function, that it rises, reaches like a small peak over here at 2, then again drops, reaches like a small dip of -2 at the point 1, and then again rises.
So
Yes.
how did we got that like y will be only increasing till 4 in the previous one?
How will be?
How did we got y is increasing only till 4 in the previous example, like 4x minus x?
How we got this now? Because we understood from the graph. Na? इसके graph में क्या nature था? That when we saw on the number line, up to 2 the function was increasing, na? And after 2 it was decreasing.
Yeah.
So it never reached infinity. You got the point, na?
So what will be the interval like when y is increasing for this function?
For this one, we've written this down. For -infinity to 2, the y is increasing, and for 2 to infinity, y is decreasing. That we already got here, no? See?
Yes, sir.
So यहाँ पे it was simple. Now up to a certain point it was increasing, and after that point it started decreasing. But here it's more complex because it increases, then decreases, and then again increases in the end. So it's starting from -infinity going back to infinity. So it's not bounded. The value of y is not bounded. It's not restricted. But in between, because it changes shape, na, from rising to dropping to rising. So there is this temporary peak point here, and there's this temporary dip point here.
Okay.
Sir,
Yes.
sir, can you scroll up
Sorry,
for a
can I?
second? Sir, can you scroll up for a second?
Yeah. Okay, this part?
Yes, sir. For a second. Sir, just a second.
Okay, just Okay, beta, the points are clear here.
Yes, sir.
Yes.
Okay, so this number line method, or what you also call baby curve method, it's clear, na, this part.
Yes, sir.
So what we are
Yes, sir.
analyzing is this quantity, x 3x square minus 3, which is factorized as this. So to understand when this is positive and when this is negative, we are separately plotting on the number line the two factors, x minus 1 and x plus 1. So the first factor is negative up to 1 and positive after that. The second factor is negative up to minus 1 and positive after that. So now we can just analyze what the product will be doing. In the region less than minus 1 is the product of two negative quantities, so it's positive. In between minus and 1 is product of positive and negative, so it's a negative quantity. And then again, it's a positive quantity. So that is about the derivative, which is the product of these two things. So what about the function? The function is increasing where the derivative is positive, so that's here and here, and then decreasing where the derivative is negative. So that's how we have an idea about the intervals, and we have this kind of idea about the shape, that the function must be rising, dropping, and then again rising. Now exactly what it is doing, so for that we have to additionally analyze at these points what is happening. So at minus 1 its value is 2, at 1 its value is minus 2, and in between at 0 its value is 0. So that means it's going from minus infinity up to 2, then dropping to minus 2, and then again rising to infinity. So this is now more or less an exact shape you can see. Okay. So as you can see, at a more advanced level, calculus or differential calculus also gives us some tools for graph plotting, of complex functions. It gives us some additional tools for plotting the graph. But as I said, over here, we will not focus so much on graph plotting. This is like extra information for us. For us, what is important is the analysis of the intervals. Now, the second thing in behavior of function, ये तो हो गया about the interval where the function is increasing and decreasing. Now, what else in the analysis of the function? So, analysis of functions. So we can use differentiation to find what is called local maxima and minima. So I'll explain this term. So application of derivative or differentiation to find the local maxima and local minimum for a function. Okay, so first of all, let's understand what is this term local maxima and minima. So we've actually already seen what a local maxima and minima is indirectly. If the graph of a function is behaving in such a way that it peaks at a point, so it basically rises, reaches a peak, and then dips, then such a point is called a local maximum. And the opposite of that, where it dips, is called the local minimum. So if this is a function y equal to fx, where what is happening is at some point, let's say x equal to a, the function is reaching like a peak point. So that peak point is called the point of local maximum. And similarly, if a function is reaching a dip at the point B, so this point over here in the graph, this is called the point of local minimum. So it is just a more technical name. You can just visualize it as peak and dip, or like a hill point and a valley point. Okay. So this is like a peak point in the graph, and this is like a dip point in the graph. Now, depending on the nature of the function, a function can have any number of maximas and any number of minimas. Okay. So for example, if you have a function whose graph looks like a wave, it can have any number of peak points, any number of dip points. You can even have a function like this, which has neither any peak nor any dip. You can have a function like this, which has only a peak and no dip. You can have a function like this, which has only a dip and no peak. So any combination of local maxima and minima is possible, including zero. There might be a function which has linear function is an example. A straight line function is one which has no local maxima and no local minima. So function can have any number of points. Including none. So examples of functions which have none, any linear function, or the function y equal to x cube. Look at the graph of y equal to x cube. It's like this. It's a curved graph, but it does not have a peak or a dip point. So it does not have any local maximum or minimum. Okay. Or y is equal to e raised power x. Go back to the graph we had drawn of e raised power x. So there are examples of this, but at the same time, it can have any number of, it can have a large number of peaks and dips also. So for example, if you visualize the graph of sine x over the entire set of values of x from minus to plus infinity. So sine x looks like a curve like this. It looks like a wave like this. So it has infinite number of local maximas and minimas. So anything is possible in general for functions. But before that, let's define a local maxima. So if a function fx rises or increases for x less than a and drops for x greater than a, then at x equal to a, the function has a peak or local maximum, and vice versa for b. If it decreases for x less than b and increases for x greater than b, then at the point b it will have a dip, and that dip point is called the local minimum. So just make a note of this definition first, then we will see how calculus comes into play or differentiation comes into play to calculate these things.
So
Yes.
So what did you write, like if a function fx rises
or increases for x less than a.
X less than, okay.
It increases for x less than a and decreases for x greater than a. Then at the point x equal to a, it has a peak point. Okay, so that is called the local maxima point.
Okay, sir.
Okay, so similarly, let's write the definition of a point of local minimum. So for example, above you can see is the point B on the graph. So if a function fx decreases for x less than b and increases for x greater than b. So at x equal to b, the function has a dip point. That point is called local minimum.
Sir, what is written after fx has a
Dip, dip, dip point or local minimum. Peak and dip, these two kind of points. Okay, now the most important thing about derivative of the function and local maxima and minima. So next thing what we'll observe is going back to the detail of the graph. So if our function was having a peak at the point A, then what we'll observe is that when we draw tangent exactly at the peak point, it will be a horizontal tangent, be a horizontal line. So tangent at x equal to A will have zero slope, and the tangent drawn at any point before that will have a positive slope. Okay, so let's say this is A minus delta x. So this has a positive slope, and if we select any point after this, the tangent has a negative slope. So additionally, at the point of local maxima x equal to A, slope of tangent at x equal to A will be 0. Okay. But slope of tangent before x equal to A will be positive, and slope of tangent after x equal to A will become negative. So you can see that how the behavior of the slope of the tangent is changing at x equal to A. The derivative here is positive, the derivative here is negative, but precisely at this point, the derivative is 0. Whereas if you see for the dip point, it is the opposite of this behavior. At this point B, the slope is 0. But if you take a point before B, the slope is negative. If you take a point after B, the slope is positive. So this is the behavior at local maxima point. Whereas now, similarly, if you analyze for local minima, but before this, the derivative is negative, and after this, the derivative is positive. Okay, so for example, going back to that same question, y is equal to, we had x cube minus 3x. The question just asked, find the values or the positions, that is values of x at which the function has local maxima or local minima. And we would have just used this concept now. So what we would have said that, okay, dy by dx, or the derivative of the function, is 3x square minus 3. Okay. So we can see that dy by dx is equal to 0. This is happening at two places, x minus 1 and x equal to plus 1. Now we can also see at x equal to 1, derivative of the function is 0, but derivative of the function at 1 minus delta x is what kind of quantity? So if you take x slightly less than 1, you can see this quantity x square minus 1 becomes negative. And the derivative of the function at 1 plus delta x, that is positive. So that means x equal to 1 is that kind of point where the function is dropping and then rising. So it must be having this kind of point. So x equal to 1 is the point of local minimum. Whereas the other point, x equal to minus 1, derivative of the function at minus 1 is 0. But what about the derivative of the function at minus 1 minus delta x? It is going to be a positive quantity. Okay. Whereas derivative of the function at minus 1 plus delta x is going to be a negative quantity. So that means now if I see the point x equal to minus 1, the function has this kind of a nature. It's rising and after that it is dropping. So the function must be having a peak at that point. Okay. So now I know from this that the shape of the graph is like this, where this peak point is at x equal to minus 1 and this dip point is at x equal to plus 1. So this is where our local minima is. And this is where our local maxima is. Okay, so this kind of analysis can be done directly on any function to understand which are the points where the graph of the function peaks or reaches local maxima and which are the points at which the graph of the function dips or reaches local minimum. Okay, so as we analyze more about this, we'll see there are a couple of more tricks that we can use to simplify or sort of develop some shortcuts for this. Okay.
So yeah, what did you take as delta x?
Delta x can be any small value, no? So you can just imagine it now. We don't need to just take some value of x slightly less than minus 1. So it's like minus 1.001 or something. So, but by putting it in the expression, you can analyze that it will become a positive value, no?
Okay.
Understood, no?
Yes, sir.
Yeah.
So in the x is equal to 1, you can take anything, any delta x is any value slightly bigger than 1.
Correct.
Okay.
So just take a point slightly to the right of that point for plus delta x and to the left of it for minus delta x. Okay, people. So with that, we come to a conclusion of today's class. Okay. So I'll send you the lecture recording and the notes and also a small exercise of questions to do based on this. And next time we will complete this part of application of differentiation. And perhaps towards the end of the class, we'll be able to start with integration also. Let's see. That's it for today's session. Thanks for attending and wish you all the best.
Thank you,
Thank you,
sir.
sir.
Thank you, sir. Bye,
Thank you,
sir.
sir. Bye, sir.
Okay, bye.